In this laboratory, you're going to determine the mechanism of a reaction that you run. You will know the starting material and you will figure out what the ending material is, and then you will try to figure out the mechanism while you're in class. The entire experiment plus your report will be done in class, and basically you have to write out a reasonable mechanism for the formation of the product before you leave. A mechanism is really just a theory of what we think is happening. We write it like this is the way it happens, and we usually have a good bit of information that substantiates why we say this, but realize a mechanism really is just a theory. You have to have a lot of experimentation, and then you develop a mechanism that makes sense according to the results of those experiments. There is a principle called Occam's razor, or Occam's razor, and basically what this is saying is the simplest explanation is most likely going to be the one that is correct. So we will run this reaction and attempt to use information to develop a mechanism, and the simplest one possible. Really, basically, when there's a lot of things you could take into effect here: how the solvents work, how are the what stereochemistry is going on there. Can you run the reaction with isotopes? And we do this a lot, but we're going to simplify this down to what is the product? What is the product? What is the reagent, and what possible mechanism would make sense under these conditions? So the most important information is what product comes from what starting material, and you have to have a pure product and a pure starting material, but this is going to be pretty straightforward, and you're going to have this here. But this is something very important, and I think you all forget this in writing mechanisms. If you have acid present in a reaction, the mechanism most likely is going to be where an electronegative atom like oxygen or nitrogen is protonated. If base is present, then most likely a protic functional group is going to be deprotonated, and that's the beginning of your mechanism. Usually acids and bases catalyze reactions, and then you can figure things out based on carbocation formation, anion formation, rearrangements, etc. So when we have unstable intermediates, sometimes we can have some surprising results. If a carbocation can form, what would happen is that carbocation can rearrange to give a different carbon structural backbone that really can confuse you. So what we will do is we will find out, can a carbocation form? Can a carbanion form? Could there be some rearrangement that occurs that would explain how the product is formed? Here's an example. Because we have acid present, we have protonation of the functional group. That protonation gives us a carbocation. Notice a methyl group shifts over right here. So we have an alkyl shift. Then water adds to the carbocation with its non-bonding pairs, and then through deprotonation you end up getting this alcohol. That's a very good example of how surprising results can form. Instead of getting a secondary alcohol here, we actually get a tertiary alcohol. Here's another example. Here's a secondary carbocation, and this hydrogen can move over a hydride shift, and it can give you a tertiary carbocation. So you have an increase in stability. Both in this reaction, you went from a secondary to a tertiary, so there's greater stability. And here we go from a secondary to a tertiary, so it's greater stability. Here You see an alkyl shift to go from secondary carbocation to tertiary is just another example. It's always that you're going to have a less stable carbocation shifts either an alkyl group or a hydrogen, a hydride, to form a more stable carbocation.